Okay, welcome to this would be week 8 in review, and week 8 we made a proper start into the second topic for level 3 chemistry, which I like to call structure, bonding, and thermochemistry. So there's 3 sections to this course based on that title. So the structure part is essentially everything to do with atomic structure and the periodic trends that we can then try to explain based on atomic structure. The second section of the course is based on bonding, so that's essentially Lewis diagrams and shapes of molecules, Lewis diagrams, and then shapes. And then the third section, T, is for thermochemistry, so this is building on the thermochem from level 2. So that's why I like to call this topics SB&T, or structure, bonding, and thermochemistry. So this first week was spent trying to teach you guys how to write electron configurations level 3 style. So in level 1, you guys would have learned that there are certain numbers of shells which orbit the positive nucleus. So I'm just going to put a large positive charge here. That represents the positive nucleus, and that is coming from the protons. And then around the positive nucleus, you guys would have arranged shells. So I want you to move away from calling these shells, and I want you to now call them energy levels, where energy is represented by the letter N. So that would be energy level 1, this would be energy level number 2, energy level number 3, and energy level number 4. So for level 3, we're particularly interested in energy levels up to number 4, because we're only interested in the atomic structure of the first 36 elements. Alright, so you guys just need to make sure you know how to do the electron configurations or write the atomic structure for the first 36 elements. And in particular, the first row of the transition metals. So the transition metals were barely touched on when you did your electron configurations in level 1. And the reasons being that a lot of these transition metals have more than 8 electrons in their outer shell, in which case the Bohr model that you guys were using when you were drawing shells just wouldn't have worked. And that's why you were only taught to do it for the first 20. So with these energy levels, there are associated orbital shapes, or orbitals, right? So you have an s orbital, a p orbital, and a d orbital. And in lesson we described how an s orbital was essentially a spherical shape, a p orbital was shaped like a dumbbell, and then a d orbital was shaped like a double dumbbell. And essentially an s orbital, so if I just do that really quickly here, an s orbital is spherical, so that's an s orbital, orbital. A p orbital was shaped like a dumbbell, so that's your p orbital. And then a d orbital was shaped like a double dumbbell, so that's the first dumbbell, and that would be the second. That's your d orbital. So as these orbitals increase in size, they can hold more electrons. Okay, so as they increase in size, they can hold more electrons, but they also take more electrons in order to become stabilized. So an s orbital can hold 2 electrons. A p orbital can hold up to a maximum of 6 electrons, and a d orbital can hold up to a maximum of 10 electrons. So the bigger the orbital, the more electrons it takes to stabilize it. Now, if we go back to my energy levels as they're arranged around the atom's nucleus here, if I just take a different color. Okay, so at energy level 1, there is only an s orbital. There's one s orbital at energy level 1. In energy level number 2, so represented by number 2, that's the energy level, you have an s orbital, and you also have a p orbital. At energy level number 3, you have an s orbital, so 3s for energy level number 3. You have a p orbital, 3p, and you have a d orbital. Then at energy level number 4, you have a 4s orbital, you have a 4p orbital, and you have a 4d orbital. Okay, now this arrangement of the orbitals, the way I've written it here, also helps explain the filling order. So this is just works out really nicely. If I now explain the filling order, alright, so the filling order, if you guys want to remember which orbital to fill the electrons into in which particular order, then this is my best way of teaching this. You fill the 1s first, represented by that arrow, then you fill the 2s next, represented by that. Then the 2p followed by the 3s. Then the 3p followed by the 4s. And then the 3d followed by the 4p. So I want to highlight this point here, the 3p, the highlighter, the 3p being followed by the 4s. That's counterintuitive. You would have thought that the 3d was filled after the 3p, but the reason the 4s is filled after the 3p is because the 4s is an s orbital which is so small, and it's easier to fill the 4s first, typically, for all elements bar copper and chromium, which we'll come back to in a minute. It's easier to fill that 4s than to go and try and fill a big 3d. So that's why you fill the 4s before you fill the 3d for the majority of the transition methods. Apart from the filling order though, although you fill the orbitals in this particular order, when you're writing them, the order is slightly different. So if we want to do the written order now, so written order, so the written order is essentially chronological order. So you write number 1 down first, then you write number 2 down, 2p, 3 comes after 2, 3p, 3d, and then comes number 4's orbitals, 4s, 4p, and 4d. So if you notice, in the written order, the 3p is here, and the 4s is there. Whereas in the filling order, the 4s appears to come directly after the 3d, the 3p rather. So that's the main difference between the filling order and the written order. So you fill your electrons into the orbitals using the filling order, but when you write down the electron configuration, you make sure that you just write the numbers chronologically. So that's how to write electron configurations. Now I have to show you an example to illustrate what I've just tried to teach there. Alright, so we'll start off with a very common element that you guys would have come across a lot in your learning up until this point. So we're just going to deal with the electron configuration for oxygen, for an oxygen atom. But I also want to introduce Hund's rule here. Hund was just a famous chemist, and he came up with this rule to tell you how to fill the orbitals when you're adding electrons to those orbitals. Now, when I'm writing electron configurations, I like to always have my filling order written here, so I can just keep an eye on what I'm doing. So always have that written just on the side of your page when you're trying to do electron configurations, so that you don't forget the correct order to do it in. So 1s, then 2s, 2p, 3s, 3p, 4s, and then go to your 3d. So for oxygen, the main thing here is to obviously know how many electrons, which comes from the atomic number 8. It's also in row 2, which tells me that I need to go down to energy level number 2 when I'm filling these electrons. So the written electron configuration for oxygen would be 1s2, 2s2, 2p. If you add up all the electrons, you have 2 plus 2, that's 4, and then 8. So that accounts for your 8 electrons with oxygen. But there's another way to represent electron configurations, and that's to use these boxes, where one box represents an s orbital. There's the 2s orbital right there, and then the 2p has the ability to hold up to 6 electrons, so we put in 3 boxes for the 2p. Now Hund's rule states that when you're filling orbitals, you put 1 electron into the orbital and then the second. So that's the 1s2. With the 2s2, the same thing. 1 electron, spin up and spin down. So electrons have spin associated with them, and they must be spinning in opposite directions if they are to be fitted into the orbital together. Otherwise, there'd be massive amount of repulsion. Now, with the 2p orbital, we have to put 4 electrons in here, and this is where Hund's rule really comes into play. You don't go like this. You don't go 1, 2, 3, 4. Right, so I've tried to use the analogy of if an electron represents a person getting onto a bus which is nearly empty. A person wouldn't typically choose to sit beside another person on an empty bus if they have a choice of sitting at an empty seat and having a bit of privacy by themselves. So the same thing works with electrons. So for Hund's rule states that instead of the electrons pairing up initially, the electrons would rather go into individual suborbitals within the p orbital. So you'd rather go like this, 1, 2, 3, and then you're forced to pair up, and that's how you fill atomic orbitals according to Hund's rule. Okay, so that's Hund's rule. The next thing I want to look at is there's a shorthand for writing electron configurations, because as you move into the transition metals and the elements with more and more electrons, you don't want to have to continuously write 1s2, 2s2, 2p, 3s2, 3p, etc. So we have a little shorthand we can use, and it's essentially based on using the noble gases. So we're going to do the shorthand electron configurations for the first row of the transition metals. So this is the electron configurations, and it's shorthand electron configurations for the first row of the transition metals. And this is where it gets interesting. This is where you typically get assessed upon. All right, so the first row of the transition metals. Well, when you're doing these, you really need to have a periodic table beside you as you perform this skill. But if you have your periodic table in front of you, the last noble gas before you head into row number 4, where the transition metals start to appear, the last noble gas is argon. So if we write down argon and put a box around it, square brackets, the square brackets mean everything as far as argon. So in other words, all the orbitals and in each energy level are filled as far as argon, and then on top of that you just need to write in the remaining part of the electron configuration for your first metal in the transition series, or the D block. So what we have here is we're going to write down 3D and then 4s, because that would be the written order. 3D comes before 4s, but according to the filling order, the 4s is filled first, so you put 2 electrons in the 4s, and then your 1 electron is left over for the 3D. That would be the electron configuration of scandium 4s. Now the next transition metal is titanium, so the same thing again, everything as far as argon. Then we write down our 3D and our 4s as in the written order, but 4s is filled before the 3D, in which case there are 2 electrons in the 4s and then 2 in the 3D. So that's for titanium. Next transition metal would be vanadium, so everything as far as argon. Write down your 3D followed by the 4s. 4s gets its 2 electrons first, and then the 3D is left with 3 electrons, so that's for vanadium. Okay, so here's where it gets a little bit interesting now. So I'm going to do this in a different color just to highlight the importance to be aware of it. Something different, red. Okay. So the next element is chromium. So we want to write down everything as far as argon. 3D comes before 4s, that's all fine. Now if we were to follow the same pattern of filling, the same filling order which we've done for every single element up until this point, we would put 2 electrons in the 4s orbital, and then that would leave us with 4 electrons in the 3D, and we would write that down on an exam paper as the electron configuration for chromium. If you do write that, you're wrong. You're going to get an X for that in your exam paper. What you need to be writing for chromium is everything as far as argon. Then you still have your 3D and your 4s in that written order. That's always going to be the same way. But instead of putting 2 electrons in the 4s, you're going to put 1. And you're going to take one of those electrons and put it into the D to give it 3D5. And that's the electron arrangement for chromium. So here comes the explanation. So if we use our boxes, we can just fit it in here. If we use our boxes to represent the orbitals, right, with 2 electrons in the 4s is stabilized, that's fine, but 3D, which is a very big orbital, like we mentioned at the start, has 1, 2, 3, 4, 5 suborbitals. And if you put your 4 electrons in there, 1, 2, 3, 4, using Hund's rule, not pairing them up unnecessarily, that would be the electron arrangement for the 3D orbital. Not very satisfied, not very stable. Whereas if you make a half-filled 3D orbital, 1, 2, 3, 4, okay, so 1, 2, 3, 4, 5. That 3D orbital is now half filled. Okay, a half-filled 3D orbital, we'll take that any day over a half-filled 4s orbital, because a 4s orbital is tiny in comparison to a 3D. So if we can essentially half stabilize our 3D orbital by simply moving that extra electron back to the 3D orbital from the 4s, then we'll take that situation, in which case that is the electron configuration for chromium, which has just disappeared to me. Just pop that back. There it is. So that is the electron configuration for chromium. Okay, we continue with our electron configurations for the remainder of the transition metals, just for completion. And there's a little bit I wanted to talk about as well, about the reason these are known as transition metals, and why transition metals have variable oxidation states and colors associated with them. So I'm just going to get a new page now. So a new page. Okay. So what we're looking at now is we're continuing with our electron configurations. Now the next element that comes up in the transition series in the first row would be everything as far as argon. We're going back to filling our 4s orbital with 2 electrons, in which case the D gets 5, and that would be for manganese. Now manganese is an interesting transition metal. You guys came up upon it a lot in level 2 and level 3 redox reactions, for the simple fact that manganese has a lot of different oxidation states, and it also has some really nice colors, really vibrant colors associated with it, so it's very useful when you're doing redox experiments. So just to give you a representation of that using the boxes, so the 3D has 5 electrons in it, so 1, 2, 3, 4, and 5, and the 4s has its 2 electrons. So manganese has 7 electrons to play with. And the reason these metals are known as transition metals is because the electrons can transition or move between orbitals. Because the 3D and the 4s are very close to each other in energy, there's not much difference in the energy levels. Electrons can easily transition from one orbital to the other. Now this transition happens just with a bit of UV light, so essentially light from natural daylight, natural sunlight. A bit of UV light can energize these electrons and move them from one orbital to the next. So when they gain that energy, they can make that jump across from one orbital to the other, but eventually energy runs out, and as it loses that energy, making its way back to its original orbital, it will emit a certain frequency, and that frequency will be equivalent to the color that you'll observe. Now the colors that we've had for manganese, if it's manganese dioxide is a green color, and the oxidation state of manganese there is +4. So in that case, there's green light which is being emitted. Another color you guys came across, if I can just find a nice representation, you had a great purple color with permanganate, MnO4-, and in that case the oxidation state of your manganese is +7. So we're showing variation in the oxidation states. And just one other example, you also had Mn2+, which was a manganese ion, and that was colorless. So that's just illustrating some of the oxidation states the manganese can have, and it's because these electrons can transition from one orbital to the other, and as they return home, they emit a certain frequency of light, which gives its characteristic colors. So that's why they're known as transition metals, because electrons can transition from one orbital to the other, and this also explains why they have variable oxidation states, and it also explains, so variable oxidation states, and it also explains the colors, or lack of. Okay, so that's just a little bit of an aside, since this used to be part of the level 3 course. As of the realignment, as far as I'm aware, this is not part of the content anymore, but it's nice to be aware of that. It's a nice little bit of understanding that fits in well with your electron configurations for transition metals. Just to continue, we're nearly through that first row of transition metals. So the next metal that comes up is iron. Again, iron has 2 oxidation states, Fe3+ and Fe2+. It is 3d6,4s2. Okay, and that is for iron. So iron is also a transition metal. So all these transition metals, bar and zinc at the end, can undergo variable oxidation states and have varied colors. Just continuing with my series here, after iron comes cobalt, so that would be 3d7 4s2 for cobalt. Then after cobalt we have nickel, which would be 3d8 4s2. Okay, that's nickel. And then comes the next anomaly or exception to the rule in this first row of the transition metals, which is copper. So if we were to follow the filling order that normally works, you would say the written order is still 3d 4s, and the filling order should be fill the 4s before the 3d, in which case you'd have 2 electrons in the 4s and then your 9 in the 3d. And that, if you write that in your assessment for the electron configuration of copper, again, you're not right. What you need to do here, same reasoning as before, it's all about stability. So instead of putting the 9 electrons in the 3d, what you want to do is you want to put 1 electron in the 4s, and then you want to put 10 in the 3d. And that's the correct electron configuration for copper. And the reason here is this is a full 3d orbital. So for the same reasons I said before, it's energetically far more stable to fill the large 3d orbital than to bother trying to fill the little small 4s orbital. So stabilize the big one first before the little one is essentially the idea here. So it is a full 3d orbital. And then just for completion, the last transition metal, which I briefly talked about, is zinc. And it is 3d10 4s2. Okay, now the reason zinc does not have no variable oxidation states, there's no colors, no color with any of the species. The only oxidation state for zinc is Zn2 plus, as you guys have seen many times, but you've never seen it as Zn plus 1 or Zn plus 3 or anything like that. So there's no variation in its oxidation state. There's no color associated with it. And the reason for that is simply because electrons cannot transition from one orbital to the other for the simple fact that both the 4s and the 3d are completely full. And that explains why zinc has no oxidation, no variation in its oxidation states and no color. And that completes our story for the transition metals. Now, there's one other thing I need to talk about, which is writing electron configurations for ions. So we're going to just finish now electron configurations of ions. And if I just take 2 examples here, we want to cover a cation, which we'll do Fe2+, and then I'll cover an anion like chloride. So the way I find the best way to teach how to write electron configuration for ions is to first get the student to write down the electron configuration for the atom. So the electron configuration of an iron atom, and we've just written it, is going to be everything as far as argon, then 3d6 4s2. Alright, now since the filling order was to fill the 4s before the 3d, then when we're forming an ion, if we're forming a positive ion, we need to remove 2 electrons. So we're removing 2 electrons because it's Fe2+. If you filled the 4s before the 3d, then you remove the electrons from the 4s before the 3d. So you remove the electrons here first from here, in which case the electron configuration for an Fe2+ ion is simply 3d6, and I'll just write in the 4s, and you've taken those electrons out of there. So that's the electron configuration for Fe2+ ions. So always remove from the 4s and then go down to the 3d. And chloride's quite straightforward. Electron configuration for the atom, first of all, for a chlorine atom, is going to be everything as far as neon, 3s2, 3p5. So you can see there, if you add up the 2 and the 5, it has 7 outer shell electrons, 7 valence electrons. Needs 1 more, so chloride has gains 1 electron, in which case the electron configuration is going to be everything as far as neon, 3s2, 3p6. And there you can see now you have your 8 valence electrons. Okay, so that's the first video that I wanted to cover for this week's work, everything to do with electron configurations. And then we took this information on electron configurations and we started to use it to try and understand the 3 periodic trends that you guys need to know for S, P, and T. So I'm going to do a second video now which introduces the periodic trends.